All right. Welcome, everybody, to the Georgia Tech Graph Theory Seminar. Our speaker today is Youngho Yoo, our own. And he's going to tell us about packing A paths and cycles in undirected group labeled graphs.
Okay, thank you, Anton. So yeah, let me start by motivating the types of problems that we'll be dealing with. And this is all joint work with Rob and Thomas. Okay, so we're interested in packing problems. So let me just define some of the terminology that'll just make things easier for us. So let F be a family of graphs. An F packing is just a set of disjoint subgraphs in F. So for example, if F is a family of cycles, then an F packing is a set of disjoint cycles in a graph. And an F hitting set is a set of vertices that intersect every subgraph that is in F. So for example, a cycle transversal, it's a set of vertices that destroy all the cycles in the graph. Okay, and instead of hitting set, people also call these a cover or a transversal, and they call this a sort of a packing covering duality. But in this talk, I'll just be using the term hitting set because covers are also used as in a slightly different manner, like cycle covers and so on. And I think hitting set is just intuitively a bit easier. Okay, so we have this obvious inequality that the maximum size of a packing in any graph is always at most the minimum size of a hitting set. Because if you have a packing of size k, then any hitting set has to contain one vertex in each of the disjoint set subgraphs. Right, so we always have this inequality, and in some very special cases we have equality here. So for example, bipartite matchings. So if your family F is just the family of a single edge, then a packing of edges is just a matching. And there's a classical theorem of Koenig that the maximum size of a matching in a bipartite graph is equal to the minimum size of a vertex cover, is the standard term. But in our terminology, it's an edge hitting set. Okay, and you know, there's a lot of beautiful theory around determining when this is satisfied with equality and so on. But these are in very special cases. And even for matchings, in general graphs, we don't have the equality, but we have this sort of an approximate equality in that the minimum size of a hitting set is always bounded by 2 times the maximum size of a packing. Okay, so we call this a sort of an approximate packing covering duality. And this is really the type of problem that we'll be focusing on in this talk. So in general, if we can bound the minimum size of a vertex cover by some function of the maximum size of a packing, then we say that the family F satisfies the Erdős-Pósa property. So if there exists some function, it doesn't matter how large the function is, if there's a function that only depends on the family such that in every graph, the minimum size of a hitting set is bounded as a function of the maximum size of the packing. Okay, and the name comes from this very famous result of Erdős-Pósa from the 60s that if you take the family to be the family of cycles, then indeed the cycles satisfy this property where f of k, the function is big O of k times log k. Okay, and so if you weren't familiar with this, then you might be wondering, like, can't you always choose the function as large as you want to satisfy this equality? There's no restriction on how large this function could be, but that is actually not the case. So the most famous example is probably the family of odd cycles. Okay, so let's take this big planar grid graph, and we add an edge between u, I, and vi for each pair. Okay, so each of these gray lines indicate one edge. So the big grid plus this non-planar edges. Right, and this is not planar, but it can be embedded on the projective plane. Right, so if you just think of a disk with the opposite points of the boundary identified, this can easily be embedded on the projective plane. And if you only look at inside this planar grid here, everything is bipartite, so there's no odd cycles there. But if you go along one of these gray edges, and go back along the grid, then you get an odd cycle. So, and in fact, the only way you get an odd cycle is if you use an odd number of these gray lines, right? So what this tells us is that this graph has an embedding on the projective plane such that a cycle is odd if and only if the cycle forms a one-sided closed curve on the projective plane. And it's very well known in topology that there's no two such cycles are disjoint. Okay, so this graph does not contain two disjoint odd cycles. So the maximum size of a packing of odd cycles is 1. But there also isn't a small hitting set. I forgot to change transcript for the hitting set. So there isn't a small hitting set. So for example, so here there are 10 vertices on each side. If you delete 9 vertices in the grid, no matter how you delete it, there will always remain an odd cycle. Okay, and you can make this grid as big as we want. So the maximum size of a packing is just 1, but the minimum size of a transversal can be arbitrarily large in relation to the size of a packing. So the family of odd cycles do not satisfy the Erdős-Pósa property. Okay, but so now let's look at some examples where they do satisfy this property. So given a vertex at A, an A cycle is just a cycle that goes through A, and an A path is a path with A meeting A exactly at its endpoints. So both endpoints of the path has to be in A, and no internal vertex can be in A. And also, I forgot to write here that an A path has to be non-trivial. It can't just be a single vertex in A. Okay, so here's a bunch of results for cycles. So Neumann-Lara showed in 84 that even cycles satisfy the Erdős-Pósa property. Thomason in 88 generalized this to show that if you give me any positive integer m, then cycles of length 0 mod m satisfy the property. And Wollan in 2011 showed that if you give me any positive integer m, then the cycles of length not congruent to 0 mod m, they also satisfy the property if and only if n is odd. Right? So if m is even, then it's just the exact same example as the odd cycle. So you take an element of order 2 in this, you take an integer such that 2 times that integer is equal to m, and you just use that as 1 in the odd cycle example. So if n is even, there's no way this could be satisfied, but if n is odd, then it is satisfied. And also A cycles that go through some fixed vertex at A, they also satisfy this property. Okay, so I mean, there's a whole industry of these Erdős-Pósa properties, and I'm only listing the ones that are relevant to this talk. But there's a lot more, and there's a recent survey that's available by Tilikos and Raymond. Okay, but now let's look at A paths. So there's a classical result of Galai that A paths satisfy the Erdős-Pósa property, and this is actually an exact result. He generalizes the Tut-Berge formula for matchings to A paths. Okay, so note that if A is your entire vertex set, then an A path is just an edge, and a packing of A path is just a matching. So you can generalize the Tut-Berge formula for matchings to A paths. That was done by Galai. And further, that can further be generalized to S paths. And so an S, okay, so here S is a partition of A, and an S path is an A path that goes between distinct parts of S. So that was shown by Motter, and again, this generalizes the Tut-Berge formula. And we'll see a further generalization of this a bit later. But let's look at A paths with other constraints. So if you give me any positive integer, even or odd, doesn't matter here, then A paths of length not congruent to 0 mod m, they satisfy the Erdős-Pósa property. And that was shown by Wollan. A paths of even length, they satisfy the property. And A path of length 0 mod 4 satisfy the property. And this is actually particularly interesting because if you give me any composite number m that's not equal to 4, then it was shown by Bruhn, Huynh, and Joos that A path of length 0 mod m do not satisfy the property. So for every composite not equal to 4, it does not satisfy the Erdős-Pósa property, but for 4, it does satisfy the property. Okay, so let's look at the example, the counterexample that shows that this is not true for composite M, that's not 4. So I'll show it for M equals 6. So again, consider this big grid, and here our A is just a set of black vertices on the left side and the right side. Okay, so now an A path has to end at the black vertices, but if you take an A path that ends with both ends on the left side, then its weight will be 2 mod 3, because you have to use 2 1s, and everything else here is a 3. So you can't get a 0 A path going like this with both endpoints on the left side. And you also can't get both endpoints on the right side. So an A path has to go across the grid. But if you don't use any of the top edges, then it'll just be, the weight will be 3. And that's not 0 in integer mod 6. So the only 0 A paths are those that go across the grid and use one of the top edges. And it's easy to see that there are no 2 such paths are disjoint, because as soon as you have one path going, one such path, that blocks off every other possible because of planarity inside this grid. And this example can be generalized to every composite that's not equal to 4. Okay, so right, so A path with length 0 mod M satisfy the Erdős-Pósa property if M is either 2 or 4, but not for all composite numbers. So of course, the remaining question is, what about the odd primes? And our first result is that if P is an odd prime, then indeed the A path of length 0 mod P satisfy the Erdős-Pósa property. Okay, and we prove this in a more general framework of undirected group labeled graphs. So first, let me describe what these are. So these are they're just undirected graphs, and we have an abelian group gamma and a mapping of the edges to the group. And the weight of a subgraph or a path or a cycle is just you just sum the edges, sum the labels of the edges in the path or a cycle. Right. Yeah. So what we do is we prove that 0 A paths in gamma labeled graphs where gamma is integers mod P, they satisfy the Erdős-Pósa property. And of course, we don't really, theoretically, we can do the whole proof without using this group terminology, but using these group labeled terminology really makes things, it really abstracts all the relevant information. And it does make things easier. And 2 of the results that I mentioned in this in the list of examples, where I said that A paths of length not congruent to 0 mod M satisfy the property, and cycles of non-zero length mod M satisfy the property if and only if M is odd. So those are actually more general as well. So they were, so Wollan was looking at them in undirected group label graphs, and he showed that gamma non-zero A paths, so they're just paths whose elements, whose labels sum to a non-zero element. They sum to non-zero. The non-zero A paths satisfy the Erdős-Pósa property, and non-zero cycles satisfy the Erdős-Pósa property if and only if the group has no element of order 2. So again, if the group has an element of order 2, then the odd cycle example gives you a counterexample. But as soon as you don't have any element of order 2, the Erdős-Pósa property is satisfied for non-zero cycle. Okay, and in this more general setting, we can actually characterize when the A paths of weight 0 in this group label setting satisfy the Erdős-Pósa property. Okay, so the only groups under which the gamma 0 A paths satisfy the Erdős-Pósa property is when the group is integers mod P or integers mod 4. These are just 2 previous theorems. And the only other group where this is satisfied is integers mod 2 to the power of some k. Okay, and to prove this last part, we actually need to go to a different setting of directed group labeled graphs. So I understand that this might be confusing because I'm giving you these slightly different definitions of labeled graphs. And again, theoretically, you can prove this without using directed group labeled graphs, but the proof would be exactly the same in directed group labeled graphs. And I want to go through the definition of this because there's an interesting problem, open problem that I want to mention after this. So in the directed model of group labeling, you orient your graph, and the rest is the same. You put an edge, for each edge you put a label in the group. Okay, but now when you calculate the weight of a path or a cycle, so more in general, if you give me a walk with this sequence of edges, you add the label of the edge if the edge is oriented in the same direction of the walk, and you subtract it if it's in the opposite direction. Okay, and so this is slightly more difficult to define, but in a lot of ways, this is actually more natural, because if you have this adding and subtracting, then if your walk sort of backtracks, then the backtracked part is always canceled out to be 0. Okay, so it has a nice cancellation property. And this, so in the directed model, you can actually use it to model, say, the homotopy type or the homology groups of a path on a surface, let's say. So in a lot of ways, this directed model is more natural. Okay, but if every element in your group has order 2, then adding and subtracting are the same. So the two models are equivalent. And so that's why we here introduce mod 2 to the power of k, we use a directed model. Okay, but I want to first mention this this beautiful result of Chodnovsky et al. That if you look at the directed group label graphs, then the gamma non-zero A paths satisfy the Erdős-Pósa property. But this is actually, again, a generalization of the Tudberge formula. So Gallite generalized it to A paths, Motter generalized that to S paths, and that can further be generalized to gamma non-zero A paths. And just by a choice of a suitable choice of the group and the labelings, you can immediately obtain the previous results and various several others. Okay, so what we prove is that gamma 0 A paths also satisfy the Erdős-Pósa property if and only if gamma is finite. So if the group is infinite, then there's no way it can be true. But if it's finite, then it's always true. And I should mention that this was independently proven by Boltz in his thesis, but this is only available in German. And we need this to prove this part. So we do give a proof of it in our paper, but I won't give a proof here. It's not too difficult. It's fairly elementary. Like the cancellation property really gives you a lot. Right, so I won't prove this theorem, but if we take this theorem for granted, then we know that 0 A paths in this group satisfy the Erdős-Pósa property, because this is just equivalent to the directed model. Okay, so first let me talk about the infinite case. So here, I mean, I'm basically assuming that the gamma is finite. What happens in the infinite case? Okay, so if the group is infinite, then I can choose some sequence of elements carefully so that I form a graph like this. So I put G1, G2 in this sequence and minus G1 in the opposite direction. So this is, again, basically the odd cycle example. Every 0 A path is forced to go from left to right, where it has to go to the opposite opposite end. And I can choose my element so that any path ending on the same side is not 0. And I always have more room to choose the next element because the group is infinite. Okay, so if the group is infinite, then there's no way it could happen. Okay, but another thing that this shows is that the Erdős-Pósa function, the function f for 0 A path, it has to grow with the size of the group. So with the previous non-zero path results, the functions there do not depend on the group at all. So in the directed case, the result of Chodnovsky, the function here is actually you either have k disjoint non-zero A paths, or you can delete the minimum size of a hitting set is actually 2 times the maximum size of a path. So this is exactly the same as matching. It generalizes the matching setting. In the undirected model, it's a bit worse. I think yeah, the best function is k to the 4. big O of k to the 4. But that again, that doesn't depend on the group. But here, the size of the function has to grow with the group, because if you give me a small function, I can give you a huge group where I can pick many of these elements. Okay, so now let's prove this characterization of 0 A paths. Okay, so we can assume that the group is finite. And if the group is one of these three, then we can use the previous theorems. And if the group is not one of these three groups, then it turns out that's exactly what you need to get a construction similar to the integers mod 6 case. Okay, so I won't go through the details here, but it turns out excluding these three groups is exactly what you need to get an example like this. Okay, and we can actually go further with this theorem. We can actually characterize, if you give me any element in the group, then I can tell you exactly when A paths of weight L satisfy the Erdős-Pósa property. And the characterization is as follows. So if L is 0, then we have these three groups as before. And if L is not 0, then the only other cases possible are when the group is integers mod 4 with L being 2, and in the case where it's integers mod P with P prime, and L can be any element. Okay, so to prove this, so again, if the group is infinite, then the same construction works. Okay, so here what makes it not work is if there exists a non-zero element G such that L is not in the subgroup generated by G. Okay, so suppose that such an element exists. Okay, then we can also form this example. So now let's take an A path that with both endpoints on the left side. Then it'll so it can use some edges here, but its total weight will be 2L plus the subgroup generated by G. It'll belong in the coset of 2L plus the subgroup generated by G. And that cannot be equal to L. If 2L plus the subgroup generated by G is equal to L, then that means L is in the subgroup. And similarly, if you have something here that's in the subgroup generated by G, so that can't be equal to L. So every A path has to go from left to right using an edge in the top row. Okay, so we may assume that if you give me any non-zero element in the group, then L is in the subgroup generated by that element. And this is a very, very strong condition to put on your group. It turns out that if your group satisfies this property, then your group actually has to be a P group for some prime P, which means every element, the order of every element is a power of a prime P. And any P group satisfying those properties is either cyclic or a generalized quaternion group. This is just a well-known fact in group theory. I mean, I didn't know it, but it appears in a lot of textbooks. So I think it seems to be very well known. Okay, but the generalized quaternion group is not abelian. So for us, this doesn't matter. So we can assume that the group is cyclic of prime power order. Okay, so we may assume that the group is cyclic and L is a non-zero element in this. So L has to have order P. Okay, and each of these cases, unless the group is equal to integers mod 2, L is going to be divisible by 2 in this group. So if P is, if the prime is odd, then you can always divide by 2. And if this is 2 to the power of A for some A larger than 1, then you can always divide by 2 because L has to be in this subgroup. And as soon as you get this property, L is equal to 2 times G for some non-zero G, this reduces to the case of 0 A paths because you take your group label graph and you take every edge incident with A and you subtract G on all those edges. Then any A path with length L that used to have length L, it now has length 0. So here this just reduces to the previous characterization of 0 A paths. Okay, so the main reason I'm mentioning all these details is because I don't know how to do this for the directed group label graphs. So can we also characterize the groups and elements such that A paths of weight L satisfy the Erdős-Pósa property? And all of the counterexamples that I mentioned, they all work. So we only have to look at these two cases, cyclic prime power groups and generalized quaternion group. So in the directed version, we don't assume that the group is abelian because this cancellation property actually works in non-abelian group as well. So it makes sense to look at non-abelian groups. So these two cases will have to be dealt with. And I'm very curious to know if these generalized quaternion groups actually have any sort of meaning in the context of Erdős-Pósa property. Yeah, so this is I think it's an interesting open question. So now let's move on to cycles, unless there are any questions. Right, so I mentioned that cycles of length 0 mod m satisfy the property, and cycles of length not congruent to 0 mod m satisfy the property if and only if m is odd. Okay, and there's actually this question of Dejter and Neumann-Lara from 1978 asking for a characterization of integers L and M such that cycles of length L mod M satisfy the Erdős-Pósa property. And in the same paper, they give an infinite family of counterexamples, but all of those examples can be sort of phrased in this way. Okay, so if you give me two integers L and M, and if the order of L is even in this group, then the Erdős-Pósa property is not satisfied. Because again, we take the odd cycle counterexample. Everything in the grid is 0, but all the gray lines have weight L. Okay, and if the order is even, then again, a cycle of weight L has to use an odd number of these gray lines. So again, they have to be one-sided closed curves on the predicted plane, and no two of them are disjoint. Okay, but if the order of L is even in integers mod m, then in particular, that implies that m has to be even. So this construction only works when m is even. So when m is odd, then there were no known results about non-zero L. So even for cycles of length 1 mod 3, this was unknown. But by looking at this more general undirected group label graphs, we were able to show that if m is an odd prime power, then if you give me any integer L, the cycles of length L mod m satisfy the Erdős-Pósa property. Okay, so this result, and also the result of A paths of length 0 mod p, they're both consequences of a structure theorem for undirected group label graphs. And to describe the structure theorem, I have to go through some graph minor theory. So before I move on, this is a great time for questions. If you've got lost in all the details, yeah, this is a great time to tune back in because it will be a very different second half of the talk. Okay, so let's go back to the definition of an Erdős-Pósa property. So we said that a family F satisfies the Erdős-Pósa property with respect to some function. If you give me any graph, either G has k disjoint subgraphs in F, or there is a small hitting set of size bounded by F. So this is a slight rephrasing of the statement that the maximum size of a packing is bounded. I mean, the minimum size of a hitting set is bounded by the maximum size of a packing. So this is just another way to define the Erdős-Pósa property. Okay, so now suppose that the family doesn't satisfy the Erdős-Pósa property with respect to this function. Okay, then that means there exists a graph that doesn't have k disjoint subgraphs in F, but also doesn't have a small hitting set of size f of k. Okay, so among all those graphs, let's say we pick a minimal counterexample where we don't really care about the graph, but we pick k to be minimal. So we say that gk is a minimal counterexample to this family satisfying the property with this function f if G doesn't have k disjoint subgraph in f, if there's no small hitting set, and subject to these two conditions, k is minimal. Okay, and this actually implies a very strong structural property of such a minimal counterexample. So for this argument, we need to assume that the family only consists of connected graphs. But let's take a small separation in your graph. So a separation is just a pair of two graphs, two subgraphs whose union is the original graph. Right. So when I say a small separation, I just mean that the part in the intersection is small. So it's a small cut. The claim is that if you give me any small separation, then exactly one side of the separation contains a subgraph in F. So if neither side contains a subgraph, then the middle part is a small hitting set. So that's a contradiction. Now suppose both sides contain a subgraph in F. Okay, so let's say A contains a subgraph in F. Now we look at the remaining graph, B minus A. If that part contains K minus 1 disjoint subgraphs in F, then we can put those together to get K disjoint subgraphs in the whole graph. So we can assume that B minus A doesn't have K minus 1 disjoint subgraphs, and A minus B doesn't have K minus 1 disjoint subgraphs. Okay, but now we're using the fact that we chose K to be minimal. So if this part doesn't have K minus 1 disjoint subgraphs, then it has a hitting set of size f of K minus 1. So A minus B has a small hitting set, B minus A has a small hitting set, and you take that, union that with the intersection, which is also small, then you get a small hitting set. Okay, so everything here is very hand wavy, but we can formalize what small means. Okay, so what this tells us is that if you give me any small separation, all the subgraphs in F are mostly contained in only one side of the small separation. It points to sort of the relevant part of the graph. And this is exactly what's called a tangle in this graph minors theory of Robertson and Seymour. Okay, so if you give me a graph, a tangle, it assigns to each small separation a direction or a part of the separation that points to the highly connected part of the graph. And it does so in a consistent way, as in it does so in sort of a tree structure. So if you have some big part that one separation points to, then this part cannot be pointed away from by another small separation. Okay, so I won't give the formal definitions here, but this can be formalized. Okay, so what the previous argument showed was that a minimal counterexample to the family satisfying the Erdős-Pósa property admits a tangle of large order such that every subgraph of G in F is in the highly connected part of the tangle. Okay, so and here highly connected isn't in the sense of K connectivity or large K, but it's in a slightly different sense. So for example, this big grid-like thing here, this is highly connected in the sense of a tangle, because there is no small separation that separates a big chunk of this wall. A small separation can only separate off a small part of this wall. Okay, so we have this sort of an abstract thing called a tangle that points to this some highly connected part of the graph that contains all the subgraphs of G in F. Okay, and again, if you're unfamiliar with this might seem very abstract, and it might not be clear how this would be useful. But one of the fundamental results of the graph minors project is the so-called grid minor theorem, which says that if you give me a large enough tangle, then I can find you some large wall. A wall is just this graph here that's highly connected to the tangle. So Like most of the wall lives in the highly connected part of the tangle. Okay, so why do we take these walls? Why don't we just take the square grids, which are obviously more natural? It's because the grids have vertices of degree 4. And in terms of graph minor relations, if you have a big grid minor, you don't necessarily have a grid as a subgraph or as a subdivision of a subgraph. But if you have a big wall, so a big wall is subcubic. So if you have a big wall as a minor, then you actually contain a subdivision of the wall in your original graph. So to make it behave nicely with the graph minor relation, we choose the subcubic version of a grid. But what's important is that it's just some kind of grid, a large grid. And actually, in some sense, this is more natural because after about a year of actually working with these walls, I realized that walls are just hexagonal grids. Right here. So take this hexagonal grid and you just sort of flatten it, it just gives you a wall. So in some sense, walls are more natural because hexagonal grids they occur more naturally than square grids. But anyway, if you have a large tangle, you have a large wall connected, highly connected tangle. Okay, and the so-called flat wall theorem of Robertson and Seymour, also called the weak graph structure theorem, says that if you give me a large wall, then I can either find you a large complete graph minor or a large piece of the wall that is flat, which I won't define here, but it means that the perimeter of the wall forms a separation, and inside the separation, this part of the graph is almost planar, roughly. Okay, so this is the flat wall theorem, and our structure theorem for undirected group label graphs is a refinement of this theorem. So we essentially start with the flat wall theorem. Let's say we obtain a KT minor. We look at how that KT minor is embedded in the original graph, and we can say things about how the cycles in that minor are distributed, the non-zero cycles with respect to the group labeling. And also with the walls, we can sort of say something about the cycles of the wall. Okay, but I won't actually list out all the cases. So I'll just give you a simplified version of this structure theorem. So if you give me an undirected group labeled graph with a very large wall, then I can either find you many non-zero cycles that are all highly connected to the wall, and it's distributed in one of 3 configurations. And I won't go into the details of how they're distributed. So either you can find many of these non-zero cycles that are highly connected to the wall, or there's a small hitting set for all the non-zero cycles that are highly connected to the wall. Right? And when I say there are many non-zero cycles, it doesn't necessarily imply that there are many disjoint non-zero cycles. So for example, this is a possible outcome of our structure theorem. You have a big wall, and you have these paths connecting the top parts of the wall going across like this. And if each of these paths are non-zero, but if they have order 2, and if everything inside this wall is 0, then you cannot find many disjoint. You can't find even 2 disjoint non-zero cycles, because this is essentially the odd cycle counterexample. So this is also can be embedded on the perspective plane. Okay, but a consequence of our structure theorem is that if in outcome 1, if you cannot find many non-zero cycles, then this has to occur. So in a sense, this odd cycle counterexample is the only obstruction for finding many disjoint non-zero cycles. Right, so yeah, everything inside the wall is non-zero. Everything inside the wall is 0. Each handle, I call this a handle because somebody saw this picture and thought it looked like a shopping bag. So each of these paths I call a handle is non-zero, but its weight has to have order 2 in the group. Okay, so an immediate consequence of this is that if the group has no element of order 2, then in the first outcome, we always have many disjoint non-zero cycles. And this immediately gives us this theorem of Wollan that I mentioned previously. So the theorem is that if gamma has no element of order 2, then gamma non-zero cycles satisfy the Erdős-Pósa property. The proof is, suppose it doesn't satisfy the Erdős-Pósa property. We take a minimal counterexample. And it has a tangle of arbitrarily large order. So we take a very, very large tangle. The grid minor theorem says it has a very large wall, highly connected to the tangle. Okay, but with this tangle, we have this additional property that every non-zero cycle is also highly connected to the tangle. Okay, so we have this large wall, and our structure theorem says in the first outcome, there are many non-zero cycles, many disjoint non-zero cycles highly connected to the wall. So in particular, we get many disjoint non-zero cycles. Okay, but what about the second outcome? The second outcome says there's a small hitting set for all the non-zero cycles in the highly connected part of the wall. But this is exactly what we need, because in this tangle, we're assuming that every non-zero cycle is highly connected to the tangle. So the second outcome is actually, it gives you actually a hitting set for all non-zero cycles in the graph. Okay, so this is in a way, it's a very technical condition here that every subgraph that we're looking at is highly connected to the tangle, but it is really crucial for proving these kinds of results. Okay, and now let's prove that if P is an odd prime, then cycles of length L mod P satisfy the Erdős-Pósa property. So the approach is the same. You take a minimal counterexample as a large tangle, gives you a large wall, and all cycles of length L mod P are highly connected to the wall. Okay, so now, of course, we use the group integers mod P. And we can assume L is not equal to 0, because if L is 0, then the result of Thomason says cycles of length 0 mod M satisfy the property for all integers M. So we can assume L is not 0. Okay, so the first outcome says there are many non-zero cycles. There are actually many non-zero disjoint cycles because P is odd. So there are no elements of order 2. And if you have such a lot of these non-zero cycles distributed in these configurations that I won't go into the details about, I can find this kind of structure, and many of these kinds of structures. So I call these non-zero cycle chains. So I have this big cycle, and I have these paths attaching to the cycle in a disjoint way, such that the weight of this path P1 is different from the weight of Q1 for all pairs. So the point of this is that I start with the cycle, and by rerouting the cycle through some of these Qs, I obtain a path. I obtain a cycle of different weight. And when we're working with integers mod P, every non-zero element is a generator of the group. So as long as I have enough of these sort of cycles attaching to the big cycle, I can get a cycle of weight L that I want. Because let's say it has P squared cycles, then I can find P of them that have where the difference is the same non-zero element. And that non-zero element generates the group. Otherwise, there's a small hitting set. So in the second outcome of this structure theorem, there's a small hitting set for the non-zero cycles highly connected to W. Right? But because we're assuming that L is not 0, there's a small hitting set for all non-zero cycles, and in particular, it hits all the cycles of weight L. So that's easy. So it's essentially the exact same proof as before, except we just have to go through the configurations and find this, show how to build this kind of structure. Which is it's not difficult, it's just routine. So I won't go through the details. Okay, but the theorem that I mentioned before is that this holds for every odd prime power. So let P be an odd prime, and let A be some natural number. and let L be any integer, then our claim is that cycles of length L mod P to the power of A, they also satisfy the Erdős-Pósa property. Okay, so again, we define this group here, and we're going to proceed by induction on the power A. So here, we're actually going to apply the structure theorem to this quotient group, modded out by the subgroup generated by P. So this quotient group will be isomorphic to integers mod P. And the reason we do this is that every element that's not in the subgroup generated by P is a generator of the whole group. So in the first outcome, we get many disjoint. Well, again, we can find this structure, but the weights of P1 and Q1 are different in the quotient group, which means that the difference is not in the subgroup generated by P. And again, so all of these differences are generators of the whole group, which means we can find many disjoint cycles of our desired weight. And in the second outcome, there's a small hitting set for non-zero cycles. Non-zero cycles that are, is there a question in the chat? Sorry. Right, so the second outcome says that the small hitting set, it hits all cycles that have non-zero weight in this quotient group. Okay, so then that means everything inside this highly connected part can actually be viewed as this subgroup labeled graph, because we can get rid of everything that's not in this subgroup. I mean, that requires some arguments, but as soon as you don't have any of these cycles that are not in the subgroup, we can assume that the group is now this subgroup labeled. But this subgroup is isomorphic to Z to the Z mod P to the A minus 1Z, so we can apply induction. Okay, so that proves this theorem. Now let's go to the A paths of length 0 mod P. So this is the first theorem that I mentioned in this talk. So again, we start with the minimal counterexample. You get a large tangle that's highly connected to all the A paths of length 0 mod P. And in the first outcome, it's very similar. I mean, instead of a cycle, you just connect 2 endpoints to A. So I didn't draw it, but it's the same. But in the second outcome, it's actually much more difficult. So what happens is that we get a small hitting set for the highly connected part of the tangle that destroys all the non-zero cycles. But what we end up is a 3 block that is gamma bipartite, which means there are no non-zero cycles. So we have this 3 block, but the vertices of A can attach to the bridges of this 3 block in very ugly ways. So this actually requires quite a bit more work, and it's actually probably the most technical part of our group. So but in this setting, under these assumptions, we can prove certain Menger type results for AB paths of weight L. But these paths, so let's say you want to prove the Erdős-Pósa property of AB paths of weight L. It doesn't actually hold in general, because you can build a counterexample very similar to the previous ones, where the AB paths have to go across the grid and have to use an edge on the top row. So it doesn't hold in general. But under this assumption, we can prove such a result. So again, I won't go into the details. So yeah, that's the end of the proof. So here I'll mention some open problems. The first one that I mentioned is to characterize the groups and elements such that A paths of weight L in directed group label graph satisfy the Erdős-Pósa property. Okay, so again, the only cases we have to consider are the cyclic groups of prime power order and generalized quaternion groups, where L is a unique element of order 2. The other one is the one posed by Dejter and Neumann-Lara to characterize all integers L and M such that cycles of length L mod M satisfy the Erdős-Pósa property. So we only proved it for the case where m is an odd prime power. Okay, so again, excluding the known results, we can assume that either m is even and the order of L is odd in this group, or n is odd and not a prime power. Okay, so there's a sort of a common pattern to these results that whenever you have an element of even order, it doesn't satisfy the property. But in all the other cases, it seems to be okay. So I would even conjecture that if I would generalize this to undirected group label graphs. So I would say maybe a possible characterization of cycles of weight L that satisfy the Erdős-Pósa property is if the order of L is odd. But this is just speculation. All right, so that's all I have. So I'll stop here. Thank you.
Thank you very much. Let us unmute ourselves and thank Youngho. Are there any questions or comments?
Youngho, I saw a paper some time ago about induced cycles that also have Erdős-Pósa property.
Yeah,
I think it was a result of Kim-Kwan. So what do you think about getting some of your results to induced cycles?
Yeah, no, those are much more difficult. So the group label setting doesn't say anything about the induced cycles. At least I don't know any way that induced cycles can be modeled as group label graphs. So, but I mean, if you're asking about induced cycles with additional group labels, yeah, that's certainly a possible direction. So maybe like induced cycles of length L mod M, for example. Yeah, that's an interesting direction.
Yeah. Okay.
Yeah, but that induced cycle result seems very, very difficult. I haven't actually read.
Yeah, it's a long paper. I know it's.
Yeah, maybe I'm one of the authors of the paper. Yeah, maybe I can comment that any family of cycles without C4 does not have the Erdős-Pósa property. We can simply make some example. So, and also I have one question. So because we had a very similar work on the undirected labeling recently. Have you thought about the half integrality for some cycles?
Yes.
Without the Erdős-Pósa property?
So in undirected group label graphs, if you in all groups, the non-zero cycles satisfy the half integral Erdős-Pósa property.
Yeah.
Or say zero weight cycles, I don't know.
Okay.
Yeah, I mean, I've been working with these counterexamples. All the counterexamples admit a half integral packing. So I suspect that the half integral Erdős-Pósa property holds for basically any family of cycles you can model as a group label graph. And I don't know any counterexamples to that, unless you know one.
Yeah, so actually, so recently, so we are motivated from this Tony, the Huynh and Wollan and Joos paper about the product of groups in the directed labeling. Yes. So they conjecture that for any fixed product of M groups, they have the half integral. And then we prove for the undirected labeling this conjecture.
Oh, I see.
Yeah, so I think
so you have arbitrarily many group labelings?
No, fixed number of groups. So the bound depends on the number of products.
Yes. Yeah. Okay. I see. Yeah, because I was thinking about the directed generalization of that, and there seems to be some natural barriers to extending their result to.
Yes, because orientation is like there are some topological problems there. We also try to prove the conjecture, but we don't prove for the directed version.
Interesting. Do you have that? Is that published or is there?
Yeah, we will submit archives soon, like in months. We are almost complete.
Thank you. Are there any more questions? If not, then let's thank the speaker again. And our next week's speaker will be Youngho Yoo, also from Georgia Tech.